What if time flew faster for you than for everyone else? Welcome to the enigmatic world of time dilation. This concept might sound like a plot from a science fiction novel, but it's a real phenomenon. Time dilation is a difference in the elapsed time as measured by two observers, owing to a relative velocity between them or to a difference in gravitational potential between their locations. If you've ever watched a sci-fi movie, you've probably come across a character who ages slower than the rest because they're traveling at nearly the speed of light or are near a massive object. This is time dilation at work. It's a mind-bending concept that has fascinated physicists and philosophers for over a century. Today, we'll be delving into the top 10 theories that try to explain this peculiar behavior of time. So, brace yourself as we dive into the depths of time and its peculiar behavior. Albert Einstein, a household name in physics, first proposed the concept of time dilation in his special theory of relativity. This mind-bending theory, introduced in the early 20th century, has reshaped our understanding of the universe and time itself. Einstein's special theory of relativity is built upon two postulates. The first is the principle of relativity, which states that the laws of physics are the same in all inertial frames. The second is the constancy of the speed of light, which posits that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. So how does time dilation factor into this? Well, according to Einstein's theory, time isn't a constant entity. Instead, it's a variable that can be affected by speed. The theory suggests that time slows down for objects moving at high speeds relative to a stationary observer. This isn't a perceptual illusion, but a fundamental aspect of the universe as real as the ground beneath our feet. Imagine a clock moving past you at a significant fraction of the speed of light. To you, the observer, the clock's ticking would appear to slow down. This isn't because the clock is faulty or there's something amiss with your perception. It's simply a direct consequence of the special theory of relativity. The faster the clock moves, the slower it ticks from your perspective. Of course, this isn't something we typically notice in our everyday lives. The speeds required for time dilation to become noticeable are far beyond what we're used to. But in the realm of high-speed particles or spaceships traveling near the speed of light, time dilation becomes a significant factor. So, according to Einstein, the faster you move, the slower time passes for you. Fascinating, isn't it? It's a concept that challenges our intuitive understanding of time, but it's a key part of the strange and wonderful world of Einstein's relativity. Gravity, a force we are all too familiar with, also plays a significant role in time dilation. It's like the invisible puppet master, subtly shaping the dance of planets and stars and even influencing the flow of time itself. This intriguing concept is rooted in Einstein's general theory of relativity, a groundbreaking work that revolutionized our understanding of the universe. So, how does gravity affect time? Well, according to Einstein's theory, the stronger the gravitational field, the slower time ticks. It's not something we'd notice in our daily lives, but in the grand theater of the cosmos, these effects can be quite significant. Imagine standing on a planet with a gravitational field much stronger than Earth's. Your wristwatch would tick slower compared to someone observing from a spaceship far away. This isn't because your watch is faulty, but because time itself is being stretched by the planet's gravity. This phenomenon, known as gravitational time dilation, is a fascinating consequence of living in a universe where space and time are intertwined. It's as if gravity is a cosmic artist, painting with broad strokes of mass and energy to bend the fabric of space-time. In this canvas, heavy objects like planets and stars create deep wells, causing time to flow slower near them. Now you might be wondering, has this been proven? Indeed, it has. Experiments conducted using precise atomic clocks have confirmed this effect. When these clocks are placed at different altitudes where the strength of Earth's gravitational field varies, they tick at slightly different rates. The clock closer to Earth, experiencing a stronger gravitational field, ticks slower than the one at a higher altitude. So what does this mean for us? Well, if you've ever wished for more time, just find a strong gravitational field. But remember, while time might slow down for you, it would be business as usual for the rest of the universe. In simple words, the stronger the gravity, the slower time passes. This is the magic and mystery of gravitational time dilation, a concept that continues to captivate and confound us as we journey through the cosmos. Time dilation is not just a theoretical concept, It's a practical issue that engineers and scientists deal with regularly. For instance, let's take a look at our Global Positioning System, or GPS. The satellites that make this system possible are moving at high speeds and are far from the Earth's surface, both factors contributing to time dilation. Due to their high velocity, these satellites experience a slight slowing down of time. On the other hand, being further from Earth's gravity means their clocks tick a bit faster. These might seem like insignificant changes, but without correcting for them, GPS systems would quickly become inaccurate. Engineers have to factor in these time dilation effects when designing GPS satellites. The onboard atomic clocks are set to tick slower than their counterparts on Earth, balancing out the effects of both gravitational and velocity-induced time dilation. Yes, time dilation is so real that we have to account for it to ensure our GPS systems work accurately. Cosmic rays, particles from space that hit our atmosphere, provide another proof of time dilation. These cosmic rays are mainly composed of high-energy particles, including a type known as muons. Now, muons are peculiar. They're unstable and typically decay in about 2/millionths of a second. However, they're moving at speeds close to the speed of light, and here's where time dilation comes into play. When observed from Earth, the muons' internal clocks seem to tick slower due to their high speed, a phenomenon known as time dilation. So even though their lifespan is incredibly short, time dilation allows these muons to journey from the upper atmosphere to the Earth's surface before they decay. In essence, the muons' high-speed travel and the resulting time dilation make their short lives seem longer to us, enabling them to reach the Earth from outer space. So time dilation helps us understand some intriguing cosmic phenomena. Imagine you have a twin and one of you travels to space at near light speed. Who would age faster? Let's dive into the thought experiment known as the twin paradox. This paradox is a fascinating illustration of the effects of time dilation, a key concept in Einstein's theory of relativity. Picture this: two twins, identical in every way. One stays on Earth while the other embarks on a journey through space, traveling at speeds close to the speed of light. According to the theory of relativity, time would pass more slowly for the twin in the spaceship compared to the twin who remained on Earth. This is the essence of time dilation. But why does this happen? Well, it all comes down to the nature of space-time. Einstein proposed that space and time are interwoven into a single continuum known as space-time. Objects moving at high speeds experience this space-time differently, causing time to slow down for them relative to stationary observers. Does this sound like science fiction? Well, it's not. This phenomenon has been tested and confirmed through numerous experiments. In one famous example, atomic clocks flown around the world on commercial flights returned showing slightly less time had passed compared to identical clocks that stayed on the ground. So back to our twins. After many years, the spacefaring twin returns to Earth. According to the laws of physics, they would find their Earth-bound sibling has aged more. They might even be greeted by a twin who is now an old man or woman, while they've barely aged at all. This is the twin paradox, a compelling demonstration of the strange and counterintuitive implications of time dilation. It's a reality that seems to defy common sense, but it is one of the fundamental truths of our universe, as strange as it may seem. In this paradox, the space-traveling twin returns younger than the one who stayed on Earth. Ponder on that as we continue our journey through the enigma of time dilation. Black holes, the most mysterious objects in the universe, also exhibit time dilation. This might sound perplexing, but let's unravel it together. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They are the ultimate manifestation of Einstein's general theory of relativity, which predicts the existence of regions where space and time are distorted by gravity to such an extent that they become almost unrecognizable. Now imagine you're watching a spaceship heading towards a black hole. As it inches closer, the clock on the spaceship appears to tick slower and slower compared to your own. This is time dilation in action, but on a cosmic scale. The stronger the gravitational field, the slower time appears to pass. This is no optical illusion or trickery. It's a fundamental aspect of our universe. The spaceship's clock slows down because the intense gravity of the black hole warps the fabric of space-time around it. This is the very essence of Einstein's theory that gravity is not a force transmitted through space, but a curvature of space-time itself. Now, let's push our imagination a bit further. As the spaceship reaches the event horizon, the boundary of the black hole from which there is no return, something even more peculiar happens. Time, as we understand it, appears to stop. For the intrepid astronaut inside the spaceship, however, time continues to pass normally. This is one of the most mind-bending predictions of Einstein's theory. But what happens beyond the event horizon, deep within the black hole, is still a mystery. The laws of physics as we know them break down, and our understanding of time and space loses its meaning. This is what makes black holes such fascinating laboratories for studying time dilation and the nature of our universe. Black holes thus serve as fascinating laboratories for studying time dilation. What happens to time at the speed of light? This question takes us into the heart of Einstein's theory of relativity. The speed of light is the cosmic speed limit, a constant throughout the universe, always clocking in at roughly 300,000 kilometers per second. But here's the kicker. According to relativity, time behaves differently for light. For a photon zipping along at the speed of light, time is a non-entity. It doesn't experience the ticking seconds, minutes, and hours that we do. It's as though time has stopped. Imagine you're that photon. You're created in a flash of energy, and in the same instant, you're absorbed somewhere else. No matter how far you travel, from your perspective, it's instantaneous. That's because at the speed of light, time dilation reaches its maximum extent. So, for a photon traveling at light speed, time essentially stands still. And that, dear viewers, is the magic and mystery of time dilation at the cosmic speed limit. Let's now explore how time dilation could affect our future. The concept of time dilation isn't just a fascinating theoretical exercise. It has real-world implications, especially when it comes to space travel. Imagine a future where we've mastered the technology to travel at speeds approaching the speed of light. At these speeds, time dilation would become a significant factor. A journey to a distant star might feel like only a few years to the travelers on board, but back on Earth, decades or even centuries could have passed. This is a concept known as the time traveler's dilemma, a journey into the future with no way back to the time they left. But it's not just about long-term space travel. Time dilation could also have implications for aging. We've all heard the saying that time flies when you're having fun. But in a world where time dilation is a reality, it could be more like time slows when you're moving fast. If you were to spend a significant amount of your life traveling at high speeds, you could potentially age slower than those who stayed behind on Earth. This could lead to a bizarre future where your twin sibling could be significantly older than you, even though you were born at the same time. And then there's the issue of communication. If we ever establish colonies on distant planets, time dilation could pose a significant challenge for communication. Messages sent from Earth to a spaceship traveling at high speeds would appear to be coming in very slowly, and vice versa. This could make real-time communication across vast cosmic distances virtually impossible. These are just some of the ways that time dilation could impact our future. As we continue to push the boundaries of science and technology, we may need to grapple with these and other implications of time dilation. But as daunting as these challenges may seem, they also open up a world of exciting possibilities. Time dilation, thus, could play a crucial role in our cosmic aspirations. Time dilation, a concept that seems straight out of a science fiction novel, is a reality we live with. It's a mind-boggling concept, one that challenges our understanding of the universe and our place in it. From Einstein's special theory of relativity to the effects of time dilation in GPS satellites, each theory we've discussed today sheds new light on this enigmatic phenomenon. Gravitational time dilation and cosmic rays, the twin paradox, the influence of black holes and the speed of light. Every facet of time dilation holds profound implications for our understanding of the cosmos. As we've explored these theories, we've seen how time dilation is not just a theoretical concept, but a practical reality that influences our daily lives and may shape the future of space travel. As we continue to explore the cosmos, the mysteries of time dilation promise to keep us intrigued. As we unravel the mysteries of time dilation, we realize the vastness of the universe and the infinite possibilities it holds. It's a journey of discovery, and we're glad you're with us on this exciting adventure. If today's exploration of time dilation has piqued your curiosity and you've learned something new, show your support by giving this video a like. We'd love to hear your thoughts, ideas, and questions about time dilation. Do you think time travel could become a reality in the future? How do you envision the implications of time dilation affecting our lives? Share your opinions in the comments section below. Remember, every like, comment, and share helps us bring more such fascinating content your way. So don't forget to hit the subscribe button and press the bell icon to stay updated with our latest videos. And finally, if you found this video enlightening, do share it with your friends and family. Who knows, you might spark a curiosity in them, and together we can continue this journey of discovery. Until next time, keep exploring, keep questioning, and keep learning.